Thousands of tons of steel, concrete, and moving vehicles hang suspended across a canyon nearly 2 kilometers wide. No pillars rise from below, no mountains support the center. A structure of this immense mass, floating entirely over empty space, contradicts our basic physical intuition. The constant downward pull of the Earth should easily drag the roadway into the canyon. For most of human history, that exact physical barrier kept trade routes limited and empires divided by deep valleys. The challenge was figuring out how to bypass the physical laws of nature that made spanning these distances mathematically impossible. Crossing absolute distance requires an approach that abandons brute strength and instead manipulates the geometry of physics. The earliest engineering solution was straightforward. Builders laid a rigid horizontal block of wood or stone across a gap. As this cross-section shows, downward forces concentrate heavily at the unsupported center point.
Double the span length and bending forces multiply rapidly. Building thicker beams creates a trap. Eventually, the structure becomes so heavy its mass overwhelms its capacity. This vicious cycle of self-weight acted as a hard physical limit for centuries, restricting how far human infrastructure could reach. To cross wider gaps, engineers had to stop fighting stiffness directly and start asking a different question. How can we make heavy loads travel differently? Look at the geometry in these historic stone arches. Instead of absorbing downward bending forces, the curve actively redirects those loads outward and down as compression, driving the weight straight into the thick stone pillars. Mastering this technique allowed the Roman Empire to string stacked repetitions of these arches together, scaling their heavy infrastructure across previously impassable valleys. But stone carries an absolute physical limitation. While it performs perfectly under compression, it crumbles when subjected to pulling forces, known as tension. Total span distances remained strictly capped. To cross extreme bodies of water, builders required a material that thrives under the exact opposite physical force. Modern structural engineering isolates forces. It assigns specific materials to perform only the tasks they are perfectly suited for. In this wireframe blueprint of a suspension bridge, the glowing main cables map the exact path of tension. Woven steel handles pulling forces incredibly well, carrying the suspended roadway while resisting the downward drag of the deck. Those cables then transfer the gathered load to the vertical towers. The towers handle pure compression, receiving the massive weight and pushing it straight down into the earth. Because cables handle horizontal distance with far less mass than rigid beams, spans once calculated as entirely impossible became achievable. By dissecting invisible lines of force, engineers broke the mass trap, pushing infrastructure over deep water. But relying on tension allowed bridges to become incredibly light. Stripping away that excess weight created a terrifying new vulnerability. As the mass decreased, gravity retreated as the primary enemy, and the atmosphere itself took its place. Wind became deadly. The 1940 Tacoma Narrows collapse provided a horrifying revelation about the hidden mechanics of these extreme spans. Bridges are not dead, static objects. They are dynamic systems that vibrate, oscillate, and react continuously to fluid dynamics. The math proved the Tacoma deck could hold thousands of tons of static cargo, but when the structure caught the wind and entered resonant motion, it easily tore itself to pieces. Engineers realized that holding up weight was no longer enough. Extreme spans had to be designed to master aerodynamics and complex energy management. Today, computational analysis allows designers to simulate invisible dynamic forces, modeling billions of stress calculations before a single cable is manufactured. When crossing vast open oceans, structures face simultaneous environmental threats. Look at the porous framing on the underside of this modern steel bridge. It is profiled to let typhoons pass without catching the deck. The entire structure acts as an active defense mechanism. The giant towers are engineered to flex and absorb seismic waves during earthquakes, while the steel layouts breathe, expanding and contracting with heavy temperature shifts. The modern superspan operates as a finely tuned mechanical system, balancing competing physical laws in real time. As engineers look forward, carbon fiber composites and microscopic structural sensors are preparing to push span limits into even harsher environments.
Using digital twins, AI simulations continuously track stress nodes across a physical bridge, allowing the structure to monitor its health and diagnose fatigue instantly. It is a long technical journey from crushing heavy wooden logs to self-analyzing aerodynamic megastructures. Yet the original paradox remains. The laws of physics never paused. Humanity never actually defeated gravity. These colossal spans hang in the sky simply because we stopped fighting natural forces. We learned how gravity thinks, and we learned how to negotiate with it.